Good morning, class. Here's Chapter 2, Limits, Section 2.1, Limits of Sequences. Chapter 2, Limits, we cover the following: limits of sequences, limits of functions at infinity, limits of functions at finite numbers, limits, algebraic methods, continuity. Recall 1.6 sequences and difference equations. A sequence is a list of numbers written in a specific order, a sub 1 all the way to a sub n, first, second, and so on, the nth term of the sequence. A sub n is the general term, and n is the set of natural numbers or positive integers, 1, 2, 3 to infinity. Recursive sequence or difference equation is in the form of a sub n plus 1 f of a sub n. The next term depends on knowing the previous one or previous ones. Example, Fibonacci sequence. F sub 1 is 1, F sub 2 is 1, and F sub n is F sub n minus 1 plus F sub n minus 2. Meaning, if you want a term, pick the previous two and add them up. That's for n larger than or equal to 3. So if I want the next one, I add these two, I get 34. Arithmetic sequence, you just add a constant. So a sub n plus 1 is a sub n plus d. That's a recursive format. A sub n equals a sub 1 plus n minus 1 times d. That's the explicit format. Geometric sequence, you multiply by a common ratio. A sub n plus 1 is r a sub n, and a sub n equals to a sub 1 r to the power of n minus 1, recursively versus explicitly. And here's the synopsis, the summary of the limits of sequences. Limit refers to the long-term behavior of a sequence, i.e. what happens to a sub n of a sequence in a long run. Limit of a sub n as n approaches infinity equals L. That's how we read it. Limit of a sub n as n approaches infinity is L. We say that a sub n converges to L. In other words, if you can come up with any number, positive, negative, small, or large, makes no difference, then the sequence converges. A limit of a sub n as n approaches infinity is infinity, or limit of a sub n as n approaches infinity is negative infinity, or D and E does not exist. We say the sequence diverges, and to find limits, simply plug in the value and observe. We will look at examples and see how that thing works. Now, one theorem that is really handy, the limit of r to the power of n as n approaches infinity is 0 if r is between 0 and 1. In fact, if it's between negative 1 and 1 works out. And if r equals 1 is 1, and if r is larger than 1 is infinity. Just by a couple of examples to show you, if I have 1/3, if I raise it to the power of 2, becomes smaller, 1/9. And cube it, it's even smaller. That's the idea. That's why this part says ultimately it goes to 0. On the other hand, if I have 3 and square, it becomes larger, 9, and cube, it's even larger. We are looking at this part. Okay, that's easily verifiable with just a couple of examples. The limit of 1 over n to the power of p equals 0 as long as p is positive. That's one of the theorems. And when you add the terms of a geometric sequence, then we call it the geometric series. And it's the sum will be a times 1 minus r to the power of n over 1 minus r. By the way, the first term, we're going to call it just a in this format. When r is between negative 1 and 1, we're going to, if you find this and you take a limit of s sub n as n goes to infinity, it's the limit of this expression as n goes to infinity. And I hope, again, remember, r to the power of n goes to 0 if it's between negative 1 and 1. So this goes to 0. because of that. And the numerator is simply a times 1 or a divided by 1 minus r. We remember that for a geometric sequence, b sub n plus 1 is r b sub n, or b sub n is b sub 0 r to the power of n. By the way, this one is a, everybody, depending on the text, they may use a1, a0, whatever. Now, if we add a constant, everybody, what happens? For example, when you give medication to a patient, a portion remains, and then you add a constant at a time step. That's what we use this formula, which gives rise to the following solution. B sub n is b sub 0 r to the power of n plus c times 1 minus r to the power of n over 1 minus r, and of course, b sub 0 or a, depending upon the text that you're using. And I have the proof at the end. You're not responsible for it, but in case if you are interested, we will look at examples to make some sense out of this. All right, let's start with, in essence, a warm-up example. What happens to a sub n of the following sequence? Well, one way, if you want to look at the limit, you can calculate the first few and see the trend. So for example, right here, if I put 1, I get 1 over 1, which is 1. If I put 2, I get 1/2 or 0.5. If I put 3, I get 1/3. 4, I get 1/4. 10, I get 1/10. 100, you get 1 over 100, and so on. So you can see that this is getting closer and closer and to 0, and you say the limit of 1 over n as n approaches infinity is 0. And its conversion. In fact, we remember this theorem, the limit of 1 over n to the power of p as n approaches infinity is 0 for p being positive. So if you compare these two, n to what power? So p equals 1 for the 1 over n. For 1 over n, the value of p, the exponent is 1. Now, if you were to graph, for example, this means 1 comma 1. This means 2 comma 1/2 or 0.5. This means 10 comma 1 over 10 or 0.1. The graph looks like that. And I'm going to remind you, in algebra, you probably remember y equals 1 over x. The graph looks like that, where it has a vertical asymptote and a horizontal asymptote. Horizontal asymptote is the x-axis of y equal to 0. That's what it means. And eventually it runs along that. That's the concept of a horizontal asymptote. Erase my work. What about this one? If I put 1, negative 1 to the power of 1 is negative 1. If I put 2, negative 1 squared is positive. If I put 3, I get negative 1 again, and 4, I get positive 1. That means if n is odd, the answer is negative 1. If it's even, the answer is positive 1. So that means it oscillates, it alternates between the two values, negative 1 and 1. And therefore, you don't have one answer and the limit doesn't exist and it's divergence. And we write the limit of negative 1 to the power of n as n approaches infinity, dne, does not exist. That means b sub n is divergent, everybody. Now, if I were to graph, it'll look like this. Let me erase my work. So this one would be 1, negative 1. 1, negative 1. Look at this one. This one would be 2, positive 1, and so on. So that's a sinusoidal function. In fact, the limit of sine and cosine as n goes to infinity doesn't exist because they alternate, they oscillate between -1 and 1. Same thing happens here. We're going to continue. Sequential limits. A sequence A sub n has a limit L, and we write, let A sub 1, A sub 2, all the way to A sub n be a sequence, and L be a real number. We write the limit of A sub n as n approaches infinity is L. If we can make A sub n arbitrarily close to L for all n sufficiently large. We also say that A sub n converges to L. On the other hand, we write the limit of A sub n as n approaches infinity is infinity if we can make A sub n arbitrarily large for all n sufficiently large. Finally, we write the limit of A sub n as n approaches infinity is negative infinity if we can make A sub n arbitrarily negative for all n sufficiently large. And of course, these two cases, the sequences diverge in the last two cases. These are known as the limit laws. We see them in the case of functions as well as the sequence involving, n. If A sub n and B sub n are convergent sequences and C is a constant, is a number, then the limit of A sub n plus B sub n as n approaches infinity is limit of A sub n as n approaches infinity plus limit of B sub n as n approaches infinity, and the rest of it. So what are they? The limit of the sum is the sum of the limits. The limit of the difference is the difference of the limits. If you have a constant, you can take it out. The limit of constant is constant. Doesn't matter what n is because it's independent of it. And reminding you of this, the limit of 1 over n to the power of p equals 0 as n approaches infinity for p larger than 0. So we don't use limit laws a lot, but we do it from time to time, and I'll show you. For example, for this warm-up example, we remember the limit of r to the power of n as n approaches infinity depends on the base. If the base r is between -1 and 1 is 0, if the base r is 1 is 1, and if the base r is larger than 1 is infinity. So how do we approach that? First, I want you to know, if you plug in, by the way, class, if you plug in, you get 2 infinity, 2 to the power of infinity minus 1, 6 to the power of infinity. And I hope you see that the top is infinity minus 1 or simply infinity. So is the bottom. And this is what we will discuss further later on. It's called indeterminate form. That means you have to use your algebraic techniques to come up with the answer. Infinity over infinity is not simple. It could be infinity, it could be a number, it could be a 0. It's not necessarily 1. Don't think it's 1. And so having said that, the methodology is to make up two fractions here. This is 1, this is another 1. And then rewrite each. For example, this one clearly it's 2 over 6 to the power of n, or 1/3 to the power of n. And this one you can say 1 to the power of n, 6 to the power of n, which makes it 1/6 to the power of n. So we write them in this fashion. Why do we do that? Well, we're going to separate them using the limit laws. And each one, and I'm going to erase my word, each one follows that the limit of r to the power of n as n approaches infinity is 0 if r is between 0 and 1. 1/3 is between 0 and 1, so is 1/6. And the answer is 0. So in this case, limit laws can help us do the job. What about here? Again, reminding you of a couple of theorems here. You just plug in to find limits, simply plug in and observe. So this one is 2 to the power of infinity. And according to this theorem, it's infinity, which means it diverges. We do the same thing for part B. Now, a to the power of minus m is 1 over a to the power of m. Therefore, this is 1 over 2 to the power of infinity, or 1 over infinity, and therefore 0. And therefore, it converges. Another way of looking at it, class, and let me show you the second method for this one. I hope you see that you can say 2 to the power of minus 1, 2 to the power of infinity, which is 1/2 to the power of infinity, and this follows this one and becomes 0. Either way, you have to justify. You have to plug in and just justify by looking at the theorems, and that's the answer. I'm going to erase my work. This one you plug in, you get 1 over infinity, which is 0. Remember, the limit of 1 over n to the power of p as n approaches infinity is 0, as long as p is larger than 0. And remember, in this case, p equals 1. The answer is 1, therefore it converges. The limit of 2n squared plus 3n minus 1 over 5n squared minus n plus 8 as n approaches infinity. Whenever you have a rational expression and n is approaching infinity, the variable, you divide by highest degree term in the denominator, which is n squared, because if you don't, please understand, if you plug in, you get infinity over infinity. And by the way, even if it's not a rational expression, then you divide by highest value in the denominator. So division by n squared is the same as multiplication by 1 over n squared. They mean the same thing. So this one, divided by n squared is 2. This is 5. This is 3 over n. This is minus 1 over n. This is minus 1 over n squared. This is plus 8 over n squared. And all of this, each one, this goes to 0, this goes to 0, this goes to 0, this goes to 0. Because the denominator goes to infinity. So the answer is 2 over 5. And we're done. That's simple, everybody. The limit of 3n minus 1 over 7n squared minus 3n. And again, we observe n is approaching infinity. You're dealing with a fraction. So you divide by highest degree term in the denominator, n squared. And simplify. So everything gets divided by n squared. And I hope you see that. This goes to 0, this goes to 0, this goes to 0. And so you're looking at 0 over 7. And I want to emphasize that the denominator is not 0, because 0 over 0 is also indeterminate. And so what it is, 0 over any number other than 0 is 0. Over here, n is approaching infinity, you're dealing with a fraction, a rational expression. You divide by highest degree term in the denominator, namely n, and simplify. And now replace the n with infinity. When you do that, this goes to 0. Infinity over 2 or 2,000 or 2 billion is still infinity. The only thing is, if by any chance you're dividing or multiplying by a negative, it becomes negative. For example, infinity divided by -2 is negative infinity. Okay. So to give you the synopsis of this and reminding you of horizontal asymptotes, when you were finding horizontal asymptotes in algebra, in college algebra, pre-calculus, one easy way was to look at the degree. The degree are the same, so the coefficients take over. The degree of the top is smaller than the bottom, becomes 0. Remember, y equals 0. In this case, y equals 2 over 5. The degree of the numerator is larger than the degree of the denominator. You don't have a horizontal asymptote. This is the same concept. Calculate the first 8 terms and find the limit. In order to find the limit, you can calculate the first few terms. That's what they are asking. And a sub 1 is given, and a general term a sub n plus 1. So obviously, the next one is a sub 2. So if I want to get to a sub 2, I say, well, I look at this one and I say, well, n plus 1 must be 2, which means n must be 1. In other words, a sub 2 is 1 minus 1/3 a sub 1. Replace it. You get 1 minus 1/3 times 2, which means 1 minus 2/3, which means 1/3. Because this is 2/3, everybody. Now, to get a sub 3, n plus 1 must be 3. That means n must be 2. And so 1 is 1. 1 is a sub 3 is 1 minus 1/3 a sub 2. So if I plug in 1/3 in here, I get 1/3 times 1/3, which is 1 over 9. 1 minus that is 8 over 9. Now, bear in mind, the first one was given, and we found 2 more, and we showed it with details. Now, here's the table so far. Let me erase my work, everybody. And I have 1, 2, 3, 4, 5 more to go. And I hope you see this can get tedious. So it's really not that big of a deal. You must show at least 2 of them with hand, show your work with details with hand, and the rest of them, if you want to use just the graphing calculator for this part and this part only, that's fine. How do you use a graphing calculator? You can use a graphing calculator by putting a sub 1. A sub 1 happen to be 2, any number. This arrow means store it in X. Okay. So you store it in X. Then a sub n plus 1 is 1 minus 1/3 X. Because a sub n plus 1 is 1 minus 1/3 a sub n, any variable will do. Then you store that one in X. Notice what, and enter repeated. Notice what happens. You store 2 in X, then 1 minus 1/3 X into X. And you press enter, gives you 0.3. I hope you know that 1/3 is 0.3 bar, okay? And then you do it repeatedly. This is the same as this one, 0.8 bar. And then the rest of them. And when you do that, you can fill up this table. Erase my book. Just what I wanted to show you, this 0.3 bar. This is 0.8 bar. Okay. All right. Now, the last one is 0.7494. If you don't see the answer, you have to continue a couple more. The answer becomes 0.75. Okay. Now, one might not see it because this number becomes smaller, this number becomes larger, this number becomes smaller. So maybe we can't tell it's 0.75. Then you need to do just click a couple more and you'll see them, okay? And you will ultimately see that it becomes 0.75, okay? So just maybe a few. just in case. But can we prove this algebraically? And that's what we did with the last question of the previous section when I did that, and I proved that it's A over K. So here's the analytical method. Let me erase my word. Analytically, we know this says A sub n plus 1 is 1 minus 1/3 A sub n. That's what they've given us. So let's take a limit of both sides. Limit of the left equals to the limit of the right. The right side, using the limit laws, we get 1. So limit of 1 as n approaches infinity, and minus 1/3 limit of A sub n as n approaches infinity. And this is, of course, 1. Now, either the limit exists or it doesn't. They say find the limit. That means they are telling us the limit exists. If the limit exists, the limit for this guy, A sub n plus 1, and the limit for A sub n is the same. Meaning, at some point, if you continue a few more, you see that nothing changes. So the limit of A sub n plus 1 equals limit of A sub n. So what is it equal to? We don't know about x, y, z. Let's say it's L. So L over here, this is L. This is 1 minus 1/3 L. So this is L. So is this, you get L equals 1 minus 1/3 L. And we're going to move this. We make it plus 1/3 L. This is 4/3 L. If I multiply by 3/4 both sides, I get L equals 3/4, and I hope everybody knows that 3/4 is the same as 0.75. And just to quickly show you that if, again, this is just to speed up the process, you have to justify the answer at least for 2 more as we did it. So the first one is given. You have to find A sub 2 and A sub 3. And then if you want to move on with this. So in this case, number 2 was A sub 1. So we're going to store that. I'm showing you. Store it into X. Okay. And then 1 minus the parentheses 1 divided by parentheses, close parentheses, X. This is 1/3 X. Now store this in X. And if you enter, you see the first number 0.3 bar. The next one is 0.8 bar, and the next one, and the next one. And I'm going to show you a couple more. See, it oscillates between 0.76 and 0.74, then it goes to 0.75 something, 0.749. If you have doubts that the answer is 0.75, do a few more. See? It shows that the limit must be 0.75. It's and again, even if you go further, okay, definitely it indicates the answer is 0.75.